So in this video, we want to define mean square periodic random processes, and I have a small theorem. It has application in some areas, but it's not a very important class of random process because it's small. We say that x of t is mean square periodic with period of t. So we see that is very limited, but of course could have some application if you could show that x of t is equal to x of t plus 1 in mean square sense. So this means that x of t, the random variable x of t, is equal to x of t plus t in mean square sense for all t and a given t. So this is so if you have such a random process, we can easily show that a mean square random process is in the context of continuous random process it has some line spectra such that these frequencies are all multiple integer factor of omega naught. So it's kind of, they have all a common period, and CKs are random. And CKs are basically the discrete Fourier transform of your random process over one period. This integral is over one period. The proof is not very difficult. Mean of CK are 0, and then these components, they should be uncorrelated, as we have learned before. Otherwise, this is not going to be wide sensor stationary and mean square periodic. Remember that this theorem is valid when it is wide sensor stationary and mean square periodic. So we need stationarity and periodicity at the same time to have line spectra. So the proof is very easy. So you can easily calculate the autocorrelation function, and then from here you can calculate, if you have such a autocorrelation function, you can calculate this one and so on. And you can calculate also the cross correlation of these guys, and you can put the details of the math. So in that case, you get these guys to be uncorrelated. So now, when you define CK as we did in the previous slide, if you put it there, you can show that this guy is going to become 0, and this is going to be. And now here, if you replace t by t plus t, is going to give you the same random process. So the proof is very easy and so on. So mean square periodicity, as long as you have a line spectra and all these omega k is equal to k omega naught, if all of them are multiple integer factor of a common frequency, then they are mean square periodic.